Thank you very much for the invitation. I would like to thank the organizers. It's always a pleasure to be here. It's the first time I come to the Cosmocaixa, but I've been to Barcelona several times. Always enjoyed being here. What I would like to do tonight is to tell you a little bit what you've heard in the previous conferences about the existence of this mysterious form of matter in the universe that goes under the name of dark matter. What I would like to do tonight is to tell you a little bit about how we search for these particles, what kind of experiments we can build to test the existence of these particles, and hopefully also to measure the properties of these particles in the universe. Now, because I know that a fraction of you have been to the previous conferences, but some of you probably didn't. So what I would like to do basically is to say a few words about the evidence for dark matter and the type of particles that could constitute the dark matter. But I'll try to take a slightly different perspective from the one that the previous speakers have provided in their conferences. And so let me start from just asking the question, what is the universe made of? And the first thing you notice, if you go on scales that go from microscopic scales, from the DNA in our body, to the size of objects we are familiar with in our everyday life. And then if you go all the way up to astronomical scales, to planets and galaxies, everything is made by the same building blocks. Everything we see and everything we are familiar with. And these building blocks actually are quite simple. They are quarks, you might have heard of, and these quarks actually are combined in triplets, and these triplets form protons and neutrons inside atomic nuclei. So you have the atomic nuclei, which are made by protons and neutrons, which in turn are made of quarks, and then you have electrons. And with these particles, actually, you can explain all the elements in the periodic table, with these very simple building blocks, just by arranging them in different configurations and different sizes. You can explain essentially most of the universe we are familiar with. And as you have seen in the previous conferences, one of the big discoveries of cosmology in the 20th century was precisely to demonstrate that if you bring together observations on different scales in the universe, so on scales that range from rotation curves of galaxies all the way to clusters of galaxies, and then even if you go on larger scales, you go on cosmological scales, you have the cosmic microwave background you've heard about in the first lecture. And if you further add up other observations, supernovae, baryonic acoustic oscillations, anything basically that we have measured in the universe, you come up with this strange distribution of matter in the universe. You have seen a form of this pie basically in all the three previous conferences. And what this tells you is that atoms, so atomic nuclei surrounded by electrons, the ones that we just described as basically everything that surrounds us, they constitute everything that surrounds us, only make 5% of the matter energy budget of the universe. And the rest of it is in the form of this mysterious form of matter and energy, one that goes under the name of dark matter. We've heard 2 lectures on this, and another one that goes under the name of dark energy. And you've heard last week our conference on this. Now, let me take a slightly different perspective on this cosmic pie, on the fact that there are these mysterious forms of mass and energy in the universe. The specific point I want to make here is that this cosmic pie is telling us something important about what's out there in the universe. But it is sometimes misleading in the sense that one could think that this reflects something fundamental about what forms of matter and energy are in the universe. And the specific point I'm trying to make is that this particular distribution of matter and energy in the universe is correct only today, which is a specific epoch in the history of the universe. If you look back in the history of the universe, so if you go all the way from the Big Bang, which is the origin of the universe we live in, all the way to today, essentially when we perform our observations, you see that the universe underwent different phases. When shortly after the Big Bang, everything, all the mass and energy in the universe was actually dominated not by dark energy, not by dark matter, but by relativistic matter. So typically, photons and neutrinos, essentially. Then something happened right before the cosmic microwave background was produced. This is a type of radiation that we actually measure today with our telescopes. We have direct observational access to this phase of the evolution of the universe. Right before then, matter has become the dominating form of matter and energy in the universe. And so it was, basically, matter dominated everything in the universe, the budget of the universe, for many, many years, many billions of years, until very recently, and this is captured by these deviations in the shape of the universe, where basically dark energy started to dominate and the universe started accelerating. So when you see that cosmic pie, always keep in mind that that composition of the universe applies only today, now that we're performing this particular observation. If you're interested in other questions, so for instance, one of the questions, fundamental questions that cosmologists always have in the back of their mind is how structures started to form in the universe. And in particular, how do you go from a universe that was very hot and homogeneous? There was, the inhomogeneities in the universe, in the density of the universe, for instance, where it's as small as 1 part in 100,000. So the universe was really very, very homogeneous and isotropic when it started. And the question for a cosmologist is basically, how do you go from a universe that was so smooth in the early universe to the universe as we observe it today, which is made of planets and galaxies and clusters of galaxies. And if you have this specific question in your mind, that plot, that distribution of dark matter, dark energy atoms, doesn't really tell you much. What is really relevant is what was the composition of the universe where structures started to form. And actually we can calculate this quite precisely. And the picture that you get is one in which atoms were a bit more abundant, relatively, to the entire matter-energy budget of the universe. Then you had photons that were very abundant, light, essentially. And then neutrinos contributed 10%, and all the rest of it was basically dark matter. So there was, dark energy, when structures started to form, played essentially no role at all in the growth of structures. So if you want to understand how a galaxy like the Milky Way we live in formed, this distribution of matter and energy in the universe is actually more relevant than the one we typically show and we typically discuss at these conferences. I'm not saying that the previous one is not important. It is important, especially if you want to describe the evolution of the dynamics of the universe, how fast the universe expands, and in particular the fact that the expansion of the universe is accelerating now. But keep in mind that that's a time-dependent statement, and especially if you're interested in the growth of structures, you need to think in terms of dark matter, which is really the scaffolding of the universe, the structure that supports all structures in the universe. What has remained more or less constant in the history of the universe is the relative proportion of dark matter and ordinary matter. So I kind of prefer this way of presenting the evidence for dark matter, or at least the relative abundance of dark matter in the universe. Where you say basically that matter in the universe is a little bit like an iceberg, of which you see actually only the tip. Keep in mind that of this tip of the iceberg, only 1% is in the form of stars. 7% is in the form of gas in what we call the virialized structures, which means structures like the galaxy we live in or clusters of galaxies. And then you have another 7%, which is in the form of a more diffuse, hard to detect intergalactic gas. And we see, a good fraction of this ordinary matter, though not all of it. But we believe that this part of this of the diagram, of this schematic diagram, is more or less under control. But as you see, there's 85% of the matter in the universe, which is in the form of dark matter today. Okay, so if you look up at the sky and you see the stars of the Milky Way, those stars actually contribute a small fraction of the mass of the galaxy we live in, and most of the mass is actually contributed by this mysterious form of matter. So it's really something that we have to understand and characterize if we want to be able to say that we have a good, convincing explanation of what the universe is made of. And another, small point that I want to make, always to give you a slightly different perspective on things with respect to the one you've seen in previous conferences, is really that if you think about really not the universe, not the galaxy or planets, but you really think about the stuff that you see around you, which means essentially the gas in this room and the carbon atoms and the oxygen atoms in your body. All these atoms have formed very late in the history of the universe. They were not formed right after the Big Bang, like hydrogen and helium. They were built after a series of stellar explosions, essentially. So nuclear fusion and stellar explosions have led to the elements that surround us. So even in this distribution, this picture of an iceberg, the elements that make us, and the reality that surrounds us, is really the tip of the iceberg. So, one of the things that cosmology has taught us in the 20th century is that, this portion of the universe, which is made of, heavy elements, is really special. And so you can think of yourself as, something very special in the history of the universe. And this is in a sense, in a meaning that we could never have suspected in the previous centuries. So, the fact that the dark matter is out there, I think also has, changes our perspective on how we see our place in the universe. Okay, let me now move on to what do we know about dark matter. What I want to tell you is really, how we search for dark matter particles. So I would like to start by characterizing what we know, essentially, about the dark matter in the universe. And this is a 10-point test that we present to our colleagues who do particle physics when they ask, what are the required properties that are dark matter, that a new particle has to satisfy if one wants to consider it a good dark matter candidate. I will try to establish the connection with physics beyond the standard model in a minute. Some of you will have seen this in the conference of Michelangelo Mangano. So what are the properties of the dark matter particle? Well, we know a few things. So for instance, and maybe this is the most important requirement, we know how much dark matter there is out there in the universe. Okay, so we can measure the abundance of dark matter in the universe with a precision of a few percent. Okay, and that's a very stringent constraint on any theory that tries to explain dark matter in the universe. We know that dark matter must be cold. I will not discuss this in detail because it would take some time, but if you have questions, feel free to ask about any of the points that I discussed now. It must be neutral, so in particular it cannot have electric charge. It cannot have any other charge like quantum core or other things. So it must be neutral. It must be consistent with all sort of experiments and observations we have performed so far. So in particular with something we call a Big Bang nucleosynthesis, so the theory that describes how light elements like hydrogen and helium and traces of lithium were produced in the early universe. And it must be consistent with what we know about the evolution of the structure of stars and the evolution of stars. And then there's another series of requirements that basically constrain the properties of these particles, so the interactions of these particles. So we can constrain, for instance, the interaction of these dark matter particles with themselves, how strongly they interact with themselves, how strongly they interact with ordinary matter. I will come back to this point in the second part of this conference. And then they must be compatible with all sort of other astrophysical measurements, you know, the measurements of gamma rays, synchrotron emission from the galaxy, and things like that. So I will not go through the details of all this. It was just to show you that, you know, we do have some clues about the properties of dark matter. So, you know, when people come up with ideas about what dark matter is, we offer this test that, you know, so that they can check that their theory actually satisfies all observational constraints. The 10th point of this test is not strictly a physics point. You know, in principle, it is possible that nature has chosen for the dark matter a particle that only interacts gravitationally with the rest of the universe. You know, from a theoretical point of view, this is not satisfactory for many reasons, but you know, from the point of view of building a theory of dark matter, we decided to include this as a sort of a requirement, so that you can at least perform at least a thought experiment, you know, maybe 100 years from now, maybe 200 years from now, but at least in principle, it has to be possible to test the existence of these particles with an experiment you can perform on Earth. Now, the next question is there any particle that can satisfy all these constraints? And the answer is that of all the particles of the Standard Model, that you've seen, for instance, in the presentation of Mangano, none of the particles, not even the neutrinos, which are the particles that interact most weakly in the Standard Model, can satisfy all these constraints. Okay, so no particle of the Standard Model, no known particle can act as the dark matter in the universe. And, you know, if you have questions, I'll be happy to walk through this test for each of the particles of the Standard Model. So you have to resort to extensions of the Standard Model of particle physics, so new particles that are postulated to go beyond what is the known particle physics. And the problem of our field, actually, of searching for dark matter, is not that we don't have theories for dark matter. The problem is that we have too many theories. And if you ask the question, you know, what is a possible candidate for dark matter, you know, this is a partial list of candidates that have been proposed in the literature, and this list could go on, you know, for a long time, basically. So there are many, many ideas about, you know, what dark matter could be. The problem is, how do we convince ourselves that we have identified dark matter? How we convince ourselves that we have identified the particle which is responsible for all the mass out there in the universe. And when you see all these, you know, particles with exotic names, you know, sometimes, you know, if you open up a physics journal, it looks like, you know, seeing these ancient manuscripts where these, you know, ancient geographers used to put monsters on at the edge, basically, of the known land. And you know, so this is an example, for instance, from the Salter map drawn in 1260, conserved at the British Library in London. And what you see is basically a map of the Earth with at the center Jerusalem, and then all the continents, all known continents, at least known by the people who produced this map, were shown around the holy city of Jerusalem. And at the edge of what is Africa, actually here, you see that there were all these monstrous creatures. And, you know, these monstrous creatures were, in many cases, just, you know, distorted perceptions of real things. You know, sometimes people would go and see, you know, a strange animal that they had never seen, and they would try to draw it, and, you know, people would write legends about it, and so on. So the hope is that just like some of these monstrous creatures turned out to be distorted perceptions of real animals. So, for instance, you have here, you know, what turned out actually to be a real animal, an elephant, and a dragon. we hope that, at least, these observations, in some cases distort, and perhaps that we're not 100% understanding from astrophysics and cosmology. We hope at least that some of these ideas, some of these, new creatures, new particles that we are whose existence we're postulating in astrophysics and cosmology will turn out to be, even if distorted perceptions of real particles. So the game is really to try to gather enough information about the universe out there, so to go and to explore this frontier and to try to identify these dark matter particles. Now, of all the particles that I've shown in that list that was scrolling up in the previous slide, there's a big category of candidates that has attracted the attention of most scientists in the past 3 decades, actually, from around the 1980s. And this class of candidates is that of weakly interacting massive particles, also called with the acronym of WIMPs. Now, why this? It is so interesting, and why this idea of having weakly interacting massive particles is so interesting and compelling for many scientists. The idea is the following. You remember that the first requirement in that 10-point test that I was showing you is that you need to have a mechanism to produce these dark matter particles with the right abundance in the universe. And what these WIMPs do for you is basically they naturally get this abundance in the universe by processes like the ones we are very familiar with in particle physics. The idea is very simple. Imagine that these particles, these dark matter particles, existed in the early universe. Now, if these particles can annihilate into particles of the standard model, into ordinary matter, which means that 2 particles collide and their energy gets converted into particles of ordinary matter, the familiar quarks and bosons of the standard model. If this is possible, then typically, if the temperature of the universe is high enough in the early universe, this reaction will reach an equilibrium. Particles of dark matter particles will annihilate into particles of the standard model, and this reaction can go also in the other direction. Ordinary matter particles can annihilate into dark matter particles. Okay, so this is a reaction at equilibrium. Some of you will be familiar with chemical reactions and equilibrium. This is exactly the same thing played at the particle level. So if this can happen, you can calculate, and this is actually a standard exercise that we do in our cosmology courses at universities. You can calculate, actually, you can write down an equation that follows the evolution of the number density of these particles here. So you can calculate how many particles are left after after some time that this reaction goes on. And what you get, the result of this calculation is the following. If you plot the density, so how many particles you have in a fixed volume that follows the expansion of the universe, what you see is that this number density falls very, very steeply, exponentially, as we say, it's exponentially suppressed, the density of these particles. So if this annihilation, if this process was kept at equilibrium throughout the history of the universe, these particles would basically disappear completely from the universe. It would be, completely subdominant compared to any form of matter in the universe. However, what happens is that you can imagine, even without writing down equations, you can imagine what happens here. These particles are annihilating to particles of the standard model. But the universe at the same time is expanding. As you know, we live in an expanding universe. So the density of these particles is going down by a lot because of this of the expansion of the universe, and not only actually to the expansion of the universe. There's other processes that tend to deplete the density. But let's follow this reaction here as the number of particles becomes smaller and smaller. This gas of dark matter particles becomes more and more dilute. At some point, the rate for this reaction drops below the expansion rate of the universe. What it means is that you have so few of these particles around that they cannot find each other anymore. They cannot annihilate anymore with other particles of the same species. And when this happens, the number density of these particles doesn't change anymore in the universe. Okay, so in jargon we say that these particles, the abundance of this particle freezes out, and the only thing that happens, the only physical effect that tends to decrease the density of these particles is just the expansion of the universe. Okay, so what happens, as I was saying, is that the reaction rate goes down, so the density of these particles goes down until at a certain point the density of these particles, when the annihilation rate drops below the expansion rate of the universe, becomes a constant. So the number of particles, of dark matter particles, doesn't change anymore in the history of the universe. And the interesting thing is that this annihilation process is characterized by a quantity, a physical quantity, that is called the annihilation cross-section, which is essentially the probability that these particles would interact if they come close enough. And the reason why these are called weakly interacting massive particles is that if the interaction of these particles that regulates if the cross-section, so if the probability for this reaction is such that the annihilation cross-section is at the weak scale in particle physics. The weak scale is a technical term that describes electroweak interactions in the Standard Model. Then you can achieve the density, which is the one that we observed. Okay, so if it's a bit, there are several steps here, but the important take-home message in this slide is if these particles have weak interactions, then we know how to produce them in the early universe with the right abundance. And this is why these particles are so interesting, and why everybody is interested in trying to identify them. Now, if you want to visualize this from the point of view of the things you know about the Standard Model of particle physics, you can think that in the bottom part of this plot you have all the particles of the Standard Model. So all the particles that compose ordinary matter. You have the quarks here. You have the leptons, the electron, the mu, and the tau, which are the heavy cousins of the electron. And then to each of these leptons you have associated neutrinos. Then on the left you have the gauge bosons, including the Higgs boson up here. Okay, so this part of the plot describes all the physics we are familiar with. What in most theories, what happens is that there is a new scale of physics in the proposed extension of the Standard Model. There's a new scale, and basically there are partners particles associated to each particle of the Standard Model. Okay, so for quarks, for instance, in theories like supersymmetry, you have associated supersymmetric quarks. To leptons, you have supersymmetric leptons, and so on. Now the question is, this is a nice theoretical construct that kind of implements this idea of a weakly interacting massive particle. The weakly interacting massive particle incidentally arises here among the partners of these gauge bosons. If you have further questions about that, feel free to ask. The idea here is basically to try and build experiments that will allow you to measure the properties, well, first of all, the existence, and then the properties of these new particles predicted by these theories. If you can do this, you can validate your particle physics model first, and then your cosmological model that, to produce these particles in the early universe. How do you search for these particles? You can certainly try and produce these particles, these new particles, at colliders, like the Large Hadron Collider. And this is what Michelangelo Mangano told you about 2 weeks ago. I will come back to this point actually at the end of this lecture. You can have other types of searches, including indirect detection and direct detection. So what I would like to do in the second part of this presentation is to walk you through these different types of experiments, and I will try to give you an idea about the, the efforts that scientists are putting into these different types of searches. So the search for dark matter is, really everywhere on the planet, and there are experiments, for direct and indirect detection in underground laboratories, on the surface of the Earth, and in space. There are also a few satellites that have been launched in the past few years that are collecting very interesting data. Let me start from indirect detection. I want to spend maybe 5-8 minutes on each of these searches, so I try to conclude on time by 7:30. So as we say, so we have this paradigm of WIMPs. So there are these weakly interacting massive particles in the universe. We say that the number density doesn't change anymore on average in the universe. However, what you can do is, you're not interested in what happens on average in the universe. You can try and see whether, because the universe is not smoothly, the matter in the universe is not smoothly distributed. There are big galaxies and planets and stuff like that. You can try and look towards regions where the density of matter, of dark matter, is high enough that this process can happen again in the history of the universe. So we said that in the early universe, everything was smooth. At some point, the density dropped below a certain threshold. Number density doesn't change anymore. If you wait long enough, dark matter redistributes itself under the pull of gravity. We show a simulation in a second. And you can ask the question, what is the annihilation rate at the center of these big concentrations of dark matter? And what kind of ordinary matter is produced at the center of these big halos of dark matter? If you want to visualize what happens in the early, in the history of the universe, this is a simulation that shows, this is time elapsed since the Big Bang. So we are at about 1 billion years after the Big Bang. You've seen that we started from a universe that was relatively smooth at the beginning. And what's happening is that at the center of these filaments, larger and larger halos of dark matter are forming. Now, until recently, this was all we could do, basically, about the evolution of the universe, to simulate the growth of structures under the pull of gravity of basically, a form of matter that only interacts gravitationally. But if you look carefully, once the universe goes beyond, 3 or 4 billion years after the Big Bang, at the center of these structures, you can start to see something interesting happening. And what you're seeing here is basically the effect of the formation of stars. Stars form, stars explode, they inject energy in the interstellar and intergalactic medium. And what this simulation shows is basically the evolution of the density, the temperature, and the chemical evolution in cosmic structures. So using this type of simulations, we can, so we would be sitting at the center of one of these halos in here. And this is one of the galaxies, the galaxy we live in is full of these events, so, supernova explosions, stars that form, and things like that. Now, based on these simulations, you can predict what would be, for instance, the flux of photons. I told you that these particles can annihilate, dark matter particles can annihilate into ordinary matter. And in particular, they can annihilate into things that we can detect with a telescope, in particular photons, therefore light. And using these simulations, using the fact that we know where dark matter is in our galaxy, we can compute what is the flux of photons, what is the high energy light that comes from the annihilation of these particles in very dense regions of the galaxy. And this is a map of the full sky in the galactic coordinates, which are the coordinates that we use most for this type of diagrams. What you see here is basically, so the coordinates are such that the center of our own galaxy, of the Milky Way, is at the center of the map. And what you see is that because dark matter is very concentrated towards the center of the galaxy, you have a strong predicted signal of photons, of gamma rays, from the center of the galaxy, and the number of other substructures that you see here, which are the substructures of dark matter in the Milky Way. Now, until recently, we couldn't compare this prediction, this predicted flux of photons with anything. We didn't have enough data. But in 2008, the Fermi satellite was launched. NASA launched this gamma ray observatory. And since then, so for the past 7 years already, this telescope has observed the gamma ray radiation from the sky, and it has produced a map that we can actually now compare with our predicted signal of photons. And this is the map that Fermi has produced. If you remember the previous one, it doesn't look at all like that, which is fine. We know that beside dark matter, there are many astrophysical sources of gamma rays. And what you see here is actually the disk of the Milky Way, the galaxy we live in, that shines in gamma rays. There are several processes that produce this emission. And what you see also is that there are point sources at high latitude. High latitude means when you go far away from the disk of the Milky Way. And one of the most interesting results of the last few years has been the fact that several groups of authors have actually identified an excess emission from the galactic center that really looks like the type of emission you would expect from the annihilation of dark matter. Now, this is an animation that NASA produced last year when they announced the observation of this excess emission. But there have been many discussions in the community to try and figure out whether the emission that we observe has anything to do with dark matter or not. So this is one of the big questions in the field is how do we explain this excess emission essentially. And the problem with these indirect detection searches, there are many ongoing searches, even the MAGIC telescope at the Canary Islands and the future CTA that will also be placed there. We'll try to find this type of signals, but we've seen this pattern several times. And the problem with these searches is that we don't really have full control on the astrophysical signals. So if you build a detector like at the Large Hadron Collider, you know what is the energy of the particles that go in, and you can reconstruct basically and characterize the collision between two particles in great detail. When you deal with astrophysics, you don't have an experiment, you have an observation of something that is happening in a distant region of the sky, and to convince yourself that you know exactly or well enough what's happening there so that you can measure deviations from your expectations is kind of tricky. And I don't expect you to understand really the titles that I've plotted here. The only thing I wanted to draw your attention to is that there are technical papers that people are publishing in, the three of them actually date back to June of this year, where basically they're trying to figure out whether they can explain this excess emission in terms of standard astrophysics. And so that's the problem with indirect detection, and that's where we are now with these experiments. There are some interesting hints of something that might be an indication of dark matter, but it's very difficult to get convincing evidence that that's the right explanation for these signals. So let me move on to direct detection, and then I will say a few words about accelerators. The idea with direct detection is very different, and as the word says, you want to detect these particles directly through the interactions, so through the collisions basically that they produce at the center of bead detectors. So the idea is the following: you build if this dark matter paradigm is true, so if there is dark matter as we all think in the galaxy, or as we have good reasons to believe, then dark matter should be streaming through this room, for instance, with a characteristic density and with a characteristic speed of about 200 kilometers per second. And that would be about one dark matter particle, if it is in the form of WIMP, in a volume which is this big. So you can imagine this room being filled with particles that are going through you continuously at a speed of 200 kilometers per second, and with this characteristic density. Now, if that's true, if you build a sensitive enough detector, you can try to measure these interactions in which a dark matter particle kicks one of the nuclei in your detector. And what you measure is the recoil energy of the nucleus of your detector, which has been hit by a dark matter particle. And this is easy to say, but you can imagine how incredibly difficult it is to build an experimental big like this, essentially, and to measure a single nucleus, atomic nucleus, which is struck by a dark matter particle. The signal is easy to produce. We know how to measure the signals, but you can imagine that, just like dark matter, there are many other particles, standard particles, entering your detector and producing this type of event. So the key of this technique is to discriminate between the events that are not interesting, for instance, electrons and gamma rays penetrating your experiment, and dark matter-like events. And the way this is done in modern experiments, at least in the most sensitive experiments that are being performed today, is the following. They use this technology. So this vessel, you can imagine, is big like this. There's liquid xenon in the bottom part, and there's gaseous xenon in the upper part. What happens, and there's an electric field actually that which is from the top to the bottom of this experiment. If an electron or a gamma ray interacts with one of the nuclei, it will strip some of the electrons from the nucleus, and this strips these electrons, because there's an electric field, will be drifted in the top part to the gas, essentially, where they will produce another flash of light. So by comparing these two signals between electrons and WIMPs, so if you have a WIMP, for instance, that interacts with the nucleus, the number of electrons that are stripped from the nucleus is much less. And so the flash of light that it produces in the top part is going to be smaller. And by playing these tricks, so to disentangle particles like a heavy WIMP kicking the nucleus, or a very light electron that is coming and interacting with the nuclei and stripping electrons out of from the nucleus, you can be very, very sensitive to the interactions of dark matter particles. Now, the way these results are presented, because no experiment so far has found convincing evidence of dark matter ever. So people have run these experiments for 30 years. They're becoming more and more sensitive with time, but so far we don't have enough. We don't have any convincing result, claim of discovery of dark matter. The results are usually plotted like this. You have a diagram in which on the y-axis you have how strong the interaction between dark matter particles and ordinary matter is. And on the x-axis you have the mass of the dark matter particle. So all these experiments can say is that for a given mass, so for instance for a mass of 100 GeV, the interaction strength, how strongly the particle interacts with ordinary matter, cannot be larger than a certain value. Okay, so if you do this for all the masses, you build what is called an exclusion plot. So basically you rule out the possibility that dark matter has interactions of this type. And you keep looking, you build a more sensitive experiment that will go to smaller values of this interaction, and you hope that as you lower the sensitivity of these experiments, you will get to a point where you can measure finally a rate and you can discover dark matter. And the actual situation, so this was just an example, but the actual situation is this. Basically, we have the strength of the dark matter interactions in incredibly small units, zeptobarns. This is 10 to the minus 46 centimeters squared. It's really a tiny cross-section, a tiny probability for these particles to interact. So you can rule out basically the possibility that these particles interact more than once in a year in a volume of 1 ton of gas. Okay, so this is the level of sensitivity of these experiments. And this is where we are now. This LUX 2013 is the currently the best experiment, and the Xenon 1 ton, which is, as I will show you, the next big experiment, will try to improve on this cross-section. And to conclude this part, let me mention that what is currently the most, the experiment that will be in the next few weeks, the most sensitive experiment on the planet, is placed in the Gran Sasso National Laboratories under a big mountain, the Gran Sasso mountain in Italy. There are these tunnels where several scientific experiments are placed. The idea is precisely to shield them from the cosmic radiation coming from the sky, which is present also in this room and well understood and well measured. And to bring this experiment in a much more quiet environment where you can pick up the faint signal produced by dark matter hitting the nuclear of your detector. And as I was saying, the most sensitive experiment today is placed in one of those tunnels. It's called Xenon 1 ton, and it was inaugurated 2 weeks ago at the Gran Sasso laboratory. So keep this name in mind, the Xenon 1 ton name in mind. There are big expectations. Hopefully, we're going to measure an event rate, and hopefully that we can, that we can discover dark matter with these experiments. This is not guaranteed. We need to be lucky that the improvement in sensitivity allows us to get to the dark matter particles, but that's not guaranteed at all. And let me conclude this part by telling you very quickly what would happen if this experiment started to observe a number of events on top of the predicted rate of events that they expect to see in their experiment. Suppose, for instance, that Xenon 1 ton, 2 years from now, announces that you have tens or hundreds of new events which are of unexpected events that can be interpreted like dark matter. What can we say about the dark matter in the universe? Well, what happens is that in this plot, where you have, again, the probability of interaction and then the mass, instead of having an upper limit, so instead of saying, the only thing we can say about dark matter is that its interactions cannot be stronger than a certain value. At that point, if you have an event rate, you can really characterize the mass of the dark matter particle and the probability that it interacts with ordinary matter, the strength of interaction with ordinary matter. Okay, and this only if the WIMP is light enough. So if it is, if its mass is 20 or 30 times the mass of the proton, we will be in this situation. If the WIMP is heavier than that, the only thing we will be able to say is that this particle must have a mass which is larger than a certain value. So you cannot place a constraint, it must be between 20 and 70. The only thing you can say is that it must be larger than a certain value. Okay, so we've seen indirect detection, we've seen the difficulties with indirect detection, but also the fact that there are some interesting hints. We've seen direct detection, we've seen the fact that there are new, very sensitive experiments that may discover something interesting in the next few years. But we've also seen that in both cases we need additional information if we want to really characterize the dark matter particle. And this is what you can do, hopefully, at the Large Hadron Collider, starting from next year, when the results of the first results of the so-called Run 2, the run of the Large Hadron Collider at very high energy that was performed in the past few months and will continue next year, and in 2017 will be released. So the Large Hadron Collider, I guess you're more or less familiar with what that is. Big accelerator placed under the border between France and Switzerland, 27 kilometers long, and there are several experiments along the circumference of this ring in which particles are accelerated. If you've never seen the concept of the Large Hadron Collider, here's a video that explains more or less what's happening in there. Particles are injected actually from a bottle of hydrogen at the beginning, and they're injected into larger and larger accelerators. There are some pre-injectors that then inject these very highly energetic particles into the beams of the Large Hadron Collider. And what you see is that if you go down the tunnel, you will see the border between France and Switzerland here. And then, if you keep going, if you follow the protons with the quarks inside the protons, the idea is that you make them collide right at the center of these big detectors. This is the Atlas, a schematic version of the Atlas detector. You produce a collision at the center of these detectors, and what you do is basically all around the collision point, this detector is densely instrumented, and you want to reconstruct the nature of the particles produced in this collision, the direction, and the energy of each of these particles. This is an incredibly difficult problem. It's an incredibly complex problem, but experimentalists now know how to characterize, how to basically understand what are the products of these collisions in incredible detail. And the way you search for these particles at these collisions is the following. If you remember this diagram here, where you had the particles of the standard model, which is ordinary matter, in the bottom part, and if you have the new particles of the new theory in the upper part, the idea, the big idea of this searching for new physics at higher energies is that by smashing together protons, which are made of quarks, you produce particles of these hypothetical particles of the extension of the standard model. If you can do that, then you can follow what happens when these particles here decay to the lightest particle of the new theory, of these blue particles, which is precisely your dark matter particle, the weakly interacting massive particle. In the case of supersymmetry, you may have heard of the name, the neutralino. Okay, and the way you follow the decay chain is that when each of these blue particles decays into a lighter blue particle, it also produces a particle of the standard model. So if you start from one of these partners of the quarks, you produce a quark of the standard model and a particle of the new theory, an ordinary particle and a particle of the new theory, and so on, until you get to the point where you produce a particles like the lightest particle of the new theory, the WIMP, and this particle carries away a fraction of the energy, but it disappears. It cannot be detected by your experiment. So the way you detect it is by observing an imbalance in the rate, when you reconstruct all the particles that are produced in the collision, you will find an imbalance in the energy in the direction where the WIMP particle has escaped. Okay, so this missing energy searches is a way of searching for these supersymmetric particles. Now, as I said, for direct detection and indirect detection, we haven't found any evidence for WIMPs, nor of any other dark matter particle. So one question which is always in the back of the mind of people doing these searches is, could we be on the wrong track? And there's an old saying contributed to Confucius that says, it is difficult to search for a black cat in a dark room, especially when there is no cat. Okay, so we don't want to be in the position where we're not finding anything because there's nothing to be found. Okay, so we need to be to have that clearly in mind as scientists. The point I want to make here is that it is possible that these WIMPs will never be found. It is possible that dark matter has nothing to do with weakly interacting massive particles. But I want to argue that this is still a good science, and once a type of science which is worth carrying a research program that is worth carrying out. And it might be, as Huxley said once, is the great tragedy of science. The slaying of a beautiful hypothesis by an ugly fact. For some people, it's hard to accept the fact that this beautiful idea, this connection between particle physics, the weak scaling particle physics, which has this problems on its own essentially, and dark matter on the larger scales. The fact that these two are connected, it's a very powerful idea. But it is possible that it is wrong, and just like Michelson and Morley at the end of the 19th century, they performed this beautiful experiment, an interferometer that demonstrated that the ether actually was believed to exist and to be the carrier of electromagnetic waves didn't exist. So they've convincingly proven, well, not 100% convincingly, but that's a complicated story. But they've shown that at least the most simple version of the ether could not exist. There was, very interesting solid science that stimulated ideas of Lorentz, Poincaré, and then eventually led to Einstein's theory of special relativity. It is possible that this WIMPs paradigm will just demonstrate to be wrong, or will be proven wrong, and then at some point, we can really move on with new ideas. It is also possible that we will find these WIMPs at one or more of these particles. And the last thing I want to, just like we did for the Higgs, it took us 60 years to find the Higgs, but eventually we found that. The last point I want to make, if I can take 2 minutes to conclude, I want to ask a very simple question. What happens if these particles are discovered at accelerators? Okay, and the reason why I want to ask this question is that, as I've shown you, is that, in the case of indirect detection, if you see something, it's kind of difficult to say convincingly whether it is dark matter or not. If you see these particles at direct detection, yeah, maybe you can say something about the mass, but only if the mass is light enough. What happens if you see these particles at the Large Hadron Collider? And what happens if you see this particle at several of these experiments? And the risk is that we will be in the same position as the 6 blind men in the Buddhist parable, which is this very ancient tale of these blind monks touching different parts of an animal, an elephant, and being asked, what is that you're touching? And the one who grabs the tail say, oh, this is a brush. And another one touches the leg, and it says, it must be a tree or a pole. And the question is, once you have different experiments pointing to different properties of the WIMP, will we have enough information to characterize and to understand what is the underlying theory? Will we be able to identify dark matter? And I'll just make a brief comment on that. There's a lot of work and that people are putting into this direction, and the answer actually depends on what kind of animal you will have discovered if you discover something. And the only point I want to make to conclude is that ideally what you would like to do is to detect something, to build an analysis that tells you if this something is a neutralino, in my theory, is the particle that I thought about, then the fraction of dark matter, which is in the form of these particles that I predicted, would be this one. And you will draw a line, like the black line here, and you will have proven, if you can prove that this reconstructed abundance of dark matter is 100% of the dark matter in the universe, at that point, you validated your particle physics model and your cosmological model, if you can perform this program. In most cases, however, with the Large Hadron Collider, the information that you have is not good enough to perform this, and you will remain in doubt, essentially. The actual reconstruction that you can realistically perform using Large Hadron Collider only is such that you will have multiple solutions. So there will be a certain probability that this is the dark matter in the universe, but it might be that this particle contributes only 1% of the matter which is out there. What I think is important to keep in mind is that if you start to bring together all these different data, so if instead of just detecting something with the Large Hadron Collider, you bring together the data from the Large Hadron Collider with direct detection or with the indirect detection, and you perform a joint analysis, so you can really figure out the big picture. The reconstruction, this program of reconstructing the properties of dark matter, and in particular of understanding what is the contribution that these particles you have discovered make to the dark matter in the universe, will be can be performed much more precisely. And as I said, there's a big effort to try and go in that direction. And so I will conclude here. Bottom line and take-home message, there's an enormous effort actually to detect weakly interacting massive particles. There's kind of a common consensus that is emerging in the field that we should be able within a few years At the very latest, if, most people believe already at the Large Hadron Collider, others say, we might need to wait until the next generation of colliders. But we're coming to a point where we can really test this paradigm of weakly interacting massive particles. And there are two possibilities. One is to, if we don't discover anything at all at these direct detection experiments, at the accelerators, indirect detection, we can rule out this possibility, this theoretical assumption that has dominated the theoretical landscape for the past 30 years. And we can move on. And, maybe, some of the young people in this room will be the ones who will find a solution for the dark matter problem. Or we can finally discover WIMPs and open the path to a new golden era of astro and particle physics. And I'll stop here. Thank you.